A very good day to my lecturer, Dr. Shadi, and also to all my fellow friends. So for today's assignment, our group, we are going to present an assignment from the subject of electronic system. So we are from 2BERZ. So this is our assignment 1, which I'm going to go through. So this is my team members. So we have 4 of us here. So first is myself, Ganda. Second is Norzela. Third is Punitan, and also the fourth member is Farzana. So the introduction will be presented by me, myself, Nan. As we know, this project is actually focused on the design and also simulation of an electronic system. So as we know, in our current world, electronic system is very important in our modern technology, which they are used to generate, process, regulate electrical signals, and also communication, controls, and so power system. So this project we have done is to design and also to simulation of the complete electronic system. As you can see, the second one is the oscillator. This introduction is actually based on the oscillator to generate 1 kilohertz sinusoidal signal. The third one is about the filter signal, and also the fourth one is to get the output voltage. So we're going to go for the next slide. So the next one is the introduction. We have read it just now. So actually, like I said, the introduction, there is an electronic system, which is a combination of the electronic components used to generate, process, and also regulate electrical signal. So the function of these is actually the system actually generates 1 kilohertz to 20 kilohertz sinusoidal signal. So you can see this electronic system. We have a lot of applications, but I have chosen a few applications such as we have power supply, consumer electronics, industrial controls, and also communication system. So all of these communication systems, all of this is the applications that we are using electronic systems. So this is the application that daily they are using. So the main objective for our assignment is to design and simulate an electronic system. So so actually this project is actually to design and also to complete the electronic system, considering which is, like I said just now, oscillator, active low pass filter, a rectifier, and also a voltage regulator. So the next objective is to generate the process different frequency signal. And the third one is also to produce a stable 5-volt DC output. Okay, so as we know, the rectifier and the voltage regulator circuits are used to convert the AC signal into a stable DC output, which is suitable for supplying power to a 1 volt offload. So the next slide is our scope of the project. This is a very important thing, as before we start anything, the scope is a main part for the project. So the scope of the project is actually to design and simulate electronic system. The second one is analysis signal generation. The third one is to consider non-ideal component, and also fourth one is to compare simulation theoretical results. So I'll just go through. Okay, so the first part of this one is also going to present by myself. The first one, oscillator. So I'll be presenting two types of oscillator. We have oscillator 1 and also oscillator 2. So the first oscillator, okay, we have to go through the introduction of this oscillator. So oscillator is about what? So oscillator is actually an electronic circuit that generates continuous periodic signal, such as a sine and also a square. We have sine wave or square wave or triangular wave. It converts the DC energy to an AC signal at the output. So this is the overview of oscillator. So the function of oscillator, as we know, is actually to generate stable and also continuous signal. Actually, as we know, this oscillator is a periodic waveform. This oscillator produces a continuous periodic waveform without requiring an external input signal, as we know over here. The second one is to act as a signal source of an electronic system. As you know, this oscillator actually serves as the main signal generator in all the electronic circuit. So it provides input signal for the communication system, and also filters, amplifier, and also signal processing circuit. So the third one is to provide timing or clock signal for the digital system. As you know, oscillator are used to generate clock, timing signals that synchronize the operation of the digital circuits such as computer, microcontroller, and also processor. So we're going to go for the next slide. So the next slide is about the working principle. Okay, so the working principle, as you know over here, the positive and the negative feedback of this thing. So as we know, we are using the Wien bridge oscillator. It used both positive and negative feedback to generate a stable sine wave signal. So the positive feedback helps to start and maintain the oscillator oscillation, while the negative feedback stabilize the output amplitude and reduce the distortion. So the second one is about the RC frequency network. This is we're gonna see later, okay, and also the OP amplification. So this one we are using 741 IC. So we are gonna go to the next slide. Okay, we just gonna okay. So this is our oscillator one. So like I said, we have two types of oscillator. We have oscillator one and also os we have oscillator 1 and also oscillator 2. So this is the first oscillator that I'm gonna explain you. Okay, so in this oscillator you can see the left hand side, the simulation. So we have using 741 OP as the amplifier, R1 R2 C1 C2 at the circuit. So you can see at the right hand side is the output of the waveform. You can see in this output what we can see, the output voltage from the graph. You can see the voltage, the frequency from the output is 989 hertz. It's nearby to 1 kilohertz. It's almost to the 1 kilohertz. So this value is actually very close to 1 kilohertz, indicating that the Wien bridge oscillator circuit operates correctly according to the design specification. And also you must understand the waveform display on the oscilloscope is smooth and is also continuous, which it also confirms that the oscillator producing a proper AC sine wave without distortion. So the stable output occurs because the RC feedback network and amplifier gain satisfy the oscillation condition. So this one we will see in the calculation. Okay, so we just go through the simulation and also the output waveform. All right. So next, the calculation for this circuit. So the first one, we're going to calculate the frequency. So as we know, the formula is for calculate this frequency of oscillation of this Wien bridge is F equals to 1 over 2 pi RC. So what is F? F is actually the oscillation of the frequency. R stands for resistance and C stands for capacitance. So as we know, you can see the calculation. R we have 15.9 kilo ohm. C we have 10 uh, yeah 10 nanofarad. Okay, so this one we have get almost 1 kilohertz, okay, according to our calculation. So from this result that we can see, this 1 kilohertz is actually matched to the result that we get from this simulation just now. So this means, like I said again, the RC components value are selected correctly. The oscillator which can generate the required low frequency sine wave, like we can see just now in our multisim. Okay, so the next we have to calculate gain. Don't forget to calculate gain. So the formula for gain is A equals to 1 plus RF over R8. So the gain of the OP amplifier circuits, it's important to ensure the continuous of this oscillation. If the gain is too low, this is important. If the gain is too low, the oscillation will stop immediately. And if the gain is too high, the output waveform become distorted. So this one later we will see the gain if 3 is bigger than A, 3 is lesser than A, or 3 is equal than A. So this one we'll go to the next slide later. So we're going to explain first this calculation. So you can know we put back the value, the value of 1 RF. Our RF is 21 kilo ohm. Our RA is 10 kilo ohm. So we substitute the value and we'll get 3.1 3.1 okay, for the A. So you can see the calculated value we get 3.1 is slightly greater than the minimum required for this gain. Actually for this one we should get A, you should get bigger than 3, okay, but get slightly different, which is 3.1. There is no issue here. So this condition is also satisfied because 3 and 3.1 is just slightly different. So the oscillator can, so in this condition, it means the oscillator can generate continuous oscillation and you can get a very stable sine wave output is produced, and you can see just now the example I showed in the multisim. Okay, so this one is oscillator 1. So we're going to go for the next is oscillator 2. So oscillator 2 is also known as a Wayne bridge oscillator, but it is designed, okay, you can see the circuit in the multisim. It is designed to generate a higher frequency signal of approximately around 20 kilohertz. So the circuit, we are using TL081 OP amplifier. We have resistor as the picture shown below, and you can see the the waveform is over there. So I have explained, I have put the waveform over there. So it's almost we can get 20 kilohertz. If I'm not mistaken, we only get from the multisim 18 to 19 kilohertz. Actually, we should get 20, but it's already approximately to 20 kilohertz. So this means the RC network values are correct, and also the oscillator can generate the required high frequency can generate a high frequency sine wave, and also the circuit is also designed satisfied as what we want. Okay, so you have to remember the smaller capacitor value of 1 nanofarad, it also helps the oscillator to produce a much higher frequency compared to oscillator 1. So you have to see just now if you compare with oscillator 1, okay, you can see the nanofarad is the value is different. Okay, this one is much more smaller. Okay, so we're going to go for the oscillator 2 calculation part. And the same thing over here, we have to do the calculation part, the same formula. So this one we're going to measure the frequency. So here you will get the frequency, the same formula, 1 over 2 pi RC. So you will get frequency around 20 kilohertz. Okay, and the same thing you're going to do for your gain. Okay, the gain you will get the same formula, and you will get the gain which is 3.2. So actually they want the required A, you should get A is bigger than 3. Okay, but you get 3.2, which means 3.2 is larger than 3. So actually this oscillation condition is satisfied. Okay, so this means the oscillator can start oscillating successfully, and also continuous sine wave output is also has been produced. Okay, and also the output signal remains stable. So we're going to go for the gain condition. Okay, this is the part I was explaining just now to you guys. We have three types of conditions. So if your A value just now we calculate is larger than 3, is smaller than 3, you can see the first one, when the gain is lesser than 3, the amplifier cannot provide enough energy to the why is the slide moving? Okay, to the this one lah. Okay, to the RC feedback network. So as a result, the oscillation becomes weaker, the waveform amplitude decreases gradually, and also eventually the oscillation stop completely. So what do you understand from this? So this means there is no stable sine wave output is produced, and also the circuit fails to operate as an oscillator. So you're going to go for the condition number 2. Condition number 2, if the A is equal to 3. So if the A is equal to 3, the amplifier provides exactly enough energy to replace the energy lost in the RC network, and also the waveform remains stable, and the sine wave have amplitude to stay constant. So as the result, it will be continuous oscillation. Q's output waveform is smooth and stable, and also minimum distortion is produced. So this is considered A equals to 3 is the best operating condition for the oscillator. Okay, so the next one we're going to go for if A is larger than 3. So when the gain is greater than 3, when the gain is larger than 3, so oscillate the amplifier provides more energy than required. Oscillation starts easily, and also output amplitude increase rapidly. So from this one we can understand the output waveform may be distorted, clipping may occur, and the sine wave may not longer be smooth. This is very important, and that is why we are doing three comparison. And this happens because the OMP amplifier output approach its maximum supply voltage limit. So we're going to for the differences. This is the differences. Okay, this is the differences in our oscillator 1 and also oscillator 2. So we're going to do the differences lah. So as we know, oscillator 1, the gain that we get, we're going to go for the gain first. Okay, so the gain that we get in our oscillator 1, the oscillator one. Okay, we're going to go for the oscillator type first. So as we know, oscillator type, so the output frequency, the output frequency for the first of we get 1 kilohertz. For the second we get 2 kilohertz. Okay, this is the difference. Okay, as we know, both circuits are Wayne bridge oscillator, which are RC oscillator that generates sinusoidal waveform using resistor. So they do not use inductors, so there are not LC oscillators. Okay, so the second one we're going to do on RC components values. Okay, so as we know, oscillator 1 uses larger resistor, oscillator 2 uses a smaller capacitor value and also smaller resistor value. You can see the difference lah. Okay, uh, okay, so the next one is they use the first oscillator is using OPM 741. Second one is using TL081. Okay, so TL081 amplifier is much more faster. It's better for higher frequency operation. The slew rate and better performance at 20 kilohertz. But compared to 717 OP amplifier, generates purpose only and suitable for low frequency application, and it's a much slower response compared to the our oscillator number 2. So the gain difference you can see much clearer. In oscillator 1, the gain is just 3.1. Oscillator 2, which is 3.2. So actually you can see this both value actually just satisfied our oscillation condition, which is A must be larger than 3. So both is satisfy this condition. So you can see the waveform characteristics. So you can see both oscillator, so you can see the board is actually generates continuous sine wave, stable AC signals, and also a smooth periodic waveform. But however, oscillator 1 just now, we can see the waveform change more slowly, but oscillator 2 waveform changes much faster because of the higher frequency. So this is the difference that you can see. So you must know the purpose of the system in the purpose of the system in oscillator 1. Oscillator 1 generates a low frequency sine wave, okay? And also, oscillator 1 generates a low frequency signal of 1 kilohertz, and oscillator 2 generates a high frequency signal of 20 kilohertz. So these both outputs are combined before entering the active low pass filter. So you must know the low pass filter later will remove the high frequency components and allow the lower frequency signal to pass through. So that's all for today's my part. So the next part will be to my friend. Thank you so much.
Hi, I'm Fazana Nadira binti Azamshah. My matrix number is B122410621. So I would like to present about Assigment amplifier and active low pass filter. So this is the Assigment amplifier. It is a circuit that combines two or more input signal into one output signal. It uses an operation amplifier, or we call as OPM, to add the input voltage together. Because of this function, it's also known as the adder circuit. So in this project, the Assigment amplifier is used to combine signal from two oscilloscopes into one signal for further processing. So next, I will explain about the working operation of this Assigment amplifier. So this amplifier is operate in inverting mode, and the output signal are connected through the resistor to the inverting terminal into the OPM, while the non-inverting terminal is connected to the ground. So the output signal is produced is the sum of all the input signal. So next is the application of the Assigment amplifier. So Assigment amplifier is widely used in electronic circuit to combine multiple signal into one output. It is also used in precision amplifier to reduce offset error or improve signal accuracy. So besides that, some amplifiers are commonly used in audio mixer to combine sound signal from different channels into one single output signal. So it also has signal before they are sent to other circuit for further operation. So next is the calculation and the multisim result. So as you can see, the calculation and the multisim result is synced, which is the V out is -3, and for the multisim also -3. So next, I will explain about the active low pass filter. So this filter is a circuit that allows low frequency signal to pass through while reducing or blocking the high frequency signal. So this filter also use OP-amp together with resistor and capacitor. So what is the main purpose of this filter? It is to remove unwanted high frequency noise from the signal. In this project, the active low pass filter is used to filter the combined signal from the summit amplifier. So next, let's see at the frequency response of this filter. At the low frequency, this signal can pass through with little or no attenuation at all. And at the cutoff frequency, the output signals start to decrease and high frequency signals are significantly reduced by the filter. So as the result of that frequency response, this filter produce a smoother and a clearer output signal. So what is the working operation of the active low pass filter? This filter allows low frequency signal to pass through while blocking high frequency signal. The OP-amp convert the high impedance input into the low impedance output, which is improve the signal performance. The circuit response is similar to passive RC filter, but the active filter can provide better performance. Besides filtering, the circuit also provides voltage gain to increase the output signal amplitude. And there is two main type of active low pass filter. The first one is switching capacitor filter, and the second one is the continuous capacitor filter. So lastly is the calculation and multisim result for active low pass filter. So as you can see, this is the calculation for this project and the multisim result for this low pass filter.
Assalamualaikum warahmatullahi wabarakatuh and good morning for everyone. I'm Nozila binti Jamaluddin. Today I would like to present the rectifier. What is rectifier? Rectifier is electrical device that convert the AC to DC. This process is mainly electronic application for the small consumer device to large industrial power system. Why it is important? Because many electronic components and systems require DC power to operate, while power distribution systems typically use AC. Rectifier bridge this gap, enabling the widespread use the electronic device. Rectifier are used in power supplies, battery chargers, welding equipment, and various other electronic systems. They are fundamental components in the conversion and control of electrical power. The rectifier have two types. First, half-wave rectifier. Secondly, full-wave rectifier. For half-wave rectifier, is used only one diode. Is allow current to flow during only half of the AC waveform. The output DC is not very smooth and has more ripple. It usually used in low power circuit because it is simple and cheap. For full waves rectifier, we have two categories. First, for center tap. Secondly, is bridge. A center tap rectifier is type of full wave rectifier that use two diodes connected to the secondary of the center tap transformer. The input voltage is coupled through the transformer to the center tap secondary. Half of the total secondary voltage appear between the center tap and each end of the secondary winding. For full wave bridge rectifier is used for 4 diode. It does not need to center tap transformer, so that circuit can be smaller and cheaper. It gives a smooth DC output and is commonly used in power supply circuit. Now we see the half wave rectifier. Based on the illustration, a diode connected to the AC supply and the load resistor RL, forming a half wave rectifier circuit. When the sinusoidal input voltage Vin is in the positive half circle, the diode becomes forward biased and allow current to flow through the load resistor. as current flow through the RL and output voltage is flowed across the load. This output voltage follow the shape of the positive half cycle and input voltage. Therefore, during the positive alternation of the AC input, the output waveform appear as the positive half of the original sine wave. The current flow from the AC source pass through the diode and load resistor, then return through the ground path back the source. This is how the half wave rectifier convert only the positive cycle of the AC into the positive DC output. Next, we see the full wave center tap rectifier. So when you just see the illustration, full wave rectifier with center tap transformer use have two diode D1 and D2 to convert both half of the AC input into the DC output. During the positive half cycle, diode D1 is forward bias and conduct current. At the same time, diode D2 is reverse bias and diode does not conduct. The current flowed through D1 and load resistor RL producing and output the voltage across the load. During the negative half cycle, diode D2 become forward bias and conduct the current. Meanwhile, diode 1 is reverse bias. The current now flow through D2 and the load resistor RL. In both half cycle, the current flow through the RL in the same direction because of the output voltage across the load become a full wave rectified DC voltage. This means both of the positive and the negative half of the AC input are converted into the positive output pulse. Next, we see the full wave bridge rectifier. So we use the four diode to convert the AC voltage to DC voltage. During the positive half cycle, diode D1 and 2 are forward biased, so they are conduct the current. At the same time, D3 and D4 are reverse biased, so they do not conduct. Current flow through the load resistor RL and produce the positive of output voltage. During the negative half cycle, diode 3 and diode 4 become forward bias and conduct the current. Meanwhile, D1 and D2 are reverse bias. Even though the input voltage is negative, the current still flow through the RL in the same direction as before. Because the current through RL always flow in the same direction for both half cycle. The output voltage become a full wave rectified out DC output. This means both of the positive and negative half of the AC input are converted into positive output pulse. Here is comparison of rectifier between half wave and full wave. For efficiency, of course, full wave is more efficiency between the half wave. For transformer utilization, of course, full wave bridge is more excellent. For the cost, half wave is lower than full wave. For typical application, full wave bridge is used for high power application, uh, full wave center tap for medium, and half wave for low power application. For this design, we choose full wave bridge. Here, we show you the circuit design for this project. We use the bridge full wave bridge rectifier. So we have the four diodes and then we use the capacitor for reduce the ripple voltage. So here the result is by calculate and the measure. Here we show the circuit design waveform for the voltage, for current of the loads, and then is the ripple voltage.
Good morning. My name is Punithan. I will explain the working principle, applications, and calculation for voltage regulator and load circuit. A voltage regulator is an electronic circuit that maintains a constant output voltage. Its main function is to protect electronic components from voltage fluctuation. Voltage regulators are commonly used in power supplies, communication devices, and automatic systems because stable voltage is important for proper operation. The voltage regulator works using negative feedback to stabilize the output voltage. The Zener diode provides a reference voltage of 2.5 volt. Next, the amplifier compares the reference voltage with the feedback voltage. If the output voltage changes, the transistor automatically adjusts the current flow through the main stable 5 volt output. Application: voltage regulators are widely used in electronic systems such as battery management system, telecommunication equipment, industrial automation, and automotive electronic systems. These applications require the stable voltage to ensure the device operates safely and efficiently. For the calculation section, the output voltage is controlled using the reference voltage from the Zener diode and the feedback network. The calculation helps us to determine whether the circuit can maintain the required 5 volt by output. By comparing the theoretical calculation with the multisim simulation result, we can verify that the circuit works correctly or not. Load. Load is a component that uses electrical power. It converts electrical energy into useful forms such as light, heat, or motion. For example, bulb, motors, fans, and resistors. Load circuits are important because they help electrical device operate properly. In a load circuit, electrical energy flows through the complete circuit to the load component. The load then converts the electrical energy into useful output. The resistance controls the current flow, while the power depends on the voltage and resistance value in the circuit. Applications: load circuits are used in power indicator light, simple lighting circuit, circuit testing, and signal system. For the calculation, we use voltage, current, and resistance value to determine the power used by the load. This calculation helps us to understand the performance and efficiency of this circuit.
For this slide, I will explain the block diagram for our complete electronic system. First, system start with two oscillator. First oscillator generate 1 kHz sine wave, while the second oscillator generate 20 kHz sine wave. These two signals serve as the input source for the system. Next, both the signal are to send the summing amplifier. This purpose of the amplifier is to the combine signal into one composite signal. This force the output of the stage contains both the frequency component. After that, the signal pass through the active low pass filter to allow low frequency to pass while reducing the higher frequency component. It's help produce clean and smooth signal before rectification stage. Next, signal sent to the full wave bridge rectifier. This stage is convert AC signal into the pulsing DC signal. Since the output of rectifier is still ripple, a capacitor is used for reduce the ripple voltage to get smooth waveform and more stable. After that, from DC signal is passed through the voltage regulator. Its function for maintain constant output voltage for design is regulated output for 5 volts. Finally, the regulate 5-volt DC output is supplied to the load, which a rate use the power 1 watts. Oh, I would show the output of the system is regulate around 5 volts, and then the current we produce 202.843 milliamps. So we want to calculate the power is IV, so we can get 1 watt.
Conclusion: This project successfully designed it and simulated a complete electronic system that combines signal generation, signal processing, and voltage regulation stages. The system was able to produce a stable 5-volt DC output for the load. From this result, simulation values were very close to the theoretical calculation, showing that the circuit design and component selection were accurate and effective. Through this project, we gained better understanding about electronic system integration, especially in designing and analyzing circuit for stable performance. Overall, this project demonstrates the importance of proper planning, accurate calculation, and suitable component selection in achieving an efficient electronic system. Thank you.